What I want to do in this video is a calculus proof of the famous centripetal acceleration formula that tells us that the magnitude of centripetal acceleration, the actual direction will change, it's always going to be pointing inwards, but the magnitude of centripetal acceleration is equal to the magnitude of the velocity squared divided by the radius. I want to be very clear, this is a scalar formula right over here. It's talking about the magnitude of the acceleration and the magnitude of the velocity. If these were vectors, we would have arrows drawn over it. So this really, I don't want people to get confused because this is a v. This is really referring to the speed squared, and this is the magnitude. So these are all scalar quantities. So to do that, let's imagine some object. Maybe it's some object in orbit around a planet or something. So let's say that that's the planet, and that you have some object that is in orbit around the planet, and it is going in a counterclockwise direction. And so let's specify its position vector as a function of time. So let's specify its position vector as a function of time. So that is its position vector, and it's going to change as a function of time as this thing spins around. And what we're going to assume for the purposes of this, proof, I guess you could call it. Let me draw some axes over here. Let me draw some axes. So if that is our y-axis, and this is our x-axis, we're going to define theta to be the angle between the positive x-axis and our vector. So that is going to be theta. And we're going to assume that this thing is in an orbit with a radius of r. So the magnitude of our position vector, even though the direction is going to change, the magnitude of our position vector is not going to change. It's always going to have length r. So this is going in a circle of radius r. So I can write it here. The magnitude of our position vector, which is changing as a function of time, is going to be r. So how can we actually express the position vector in terms of its components at any given time? Well, we can write the position vector, and I'll do it in engineering notation. And so you might want to review those videos if some of this looks foreign. And I will do a little bit of basic trigonometry and breaking down the vector into its components. And I encourage you to review those videos if some of that looks a little bit daunting. If you take the position vector at any time, the magnitude is r. This angle is theta right over here. Its x component, I'll do the x component in blue. Its x component, this vector right over here, is going to be, the magnitude of its x component, I should say, is going to be r cosine of theta. We learned that this comes from basic trigonometry when we started, I think, in a two-dimensional projectile motion. We saw how to break these vectors down into its components. And the y component of this vector, is going to be r sine of theta. It's going to be the same thing as this vector, the magnitude right over there. So this is going to be r sine of theta. So the position vector at any time, can be written as a sum of its x and y components. So it's the magnitude of its x component is going to be r cosine of theta. And I could write theta as a function of time if I like, but I'm just going to write r cosine of, actually let me write it that way because it shows that theta is going to be a function of time. This thing is moving, and there's going to be that times the I unit vector. We're going to do engineering notation right over here. So that is the I unit vector. This tells us that that is the x component. It's going in the positive x direction, plus the magnitude of the y component, which is r sine of theta, which is going to be a function of time. So let me be clear. The function of time applies to the theta. Let me put some parentheses around it like that. And that is going in the j direction. So that is our j unit vector. So that is going in the j direction. So now we have position as a function of theta, which is actually a function of time. So let's take the derivative of this thing right over here. So what is the derivative of our position vector? The derivative of our position vector with respect to time. Well, that's just going to be our velocity vector. So that's just going to be our velocity vector as a function of time. And it's going to be equal to, we just have to take the derivative of each of these parts with respect to time. And you just do the chain rule. So you're going to have the r sit outside. That's just a constant. So you're going to have r. The derivative of cosine of theta t with respect to theta t. So I'm just doing the chain rule right over here. That's going to be negative sine of theta t. theta t. And then it's the chain rule. We also have to multiply that times the derivative of theta t, the derivative of theta of t with respect to t. So times d theta dt. This is just the chain rule right over here. And so that's going to be how it's changing in the x direction. And in the y direction, we do something very similar. In the y direction, we take the same derivative. You have the r scalar out front, r, and then the derivative of sine of theta with respect to theta is going to be cosine of theta, and I'll write it as a function of time. And then do the chain rule. You also have to multiply that times the rate at which theta is changing with respect to t, times d theta dt. And this is all going to be times our j. This is all times our j unit vector. Now, there's something that you might already realize, and you should rewatch the video on angular velocity if this is foreign to you. But d theta dt, this is our angular velocity. That's why I said to rewatch that video. This right over here, the rate at which the angle changes with respect to time, that is angular velocity. So this right over here is, that right over there is angular velocity. And for the sake of this video, and this is an assumption that we'll have to make for this formula right over here, we're going to assume that omega, which is the rate of change of our angle with respect to time, we're going to assume that this is constant. So this is an assumption that we're making for this proof. We are going to assume that omega is constant. And if omega is constant, then we can treat it literally as a constant, and we can actually factor it out of this expression. So let's actually factor out a negative omega r from this expression right over here. So we can rewrite our velocity as a function of time is equal to, I'm going to factor out a negative omega times r. And if you factor out a negative omega r, what you're left with, let me put some big brackets right over here, is this first term. The negative got factored out, the r got factored out, the omega got factored out. You just have a sine of theta t here. Sine of theta of t. So let me, and I didn't have to make it explicit that theta is a function of t, but this makes it explicit that theta is a function of t. Theta is a function of t, and then times our I unit vector, plus, so if we're factoring out a negative omega r, this becomes negative cosine of theta, which is a function of t. And that's times our j unit vector. And let me close the parentheses in the right way. So we factored out negative omega r. Now let's take the derivative of this with respect to time. So if we take, and let me give myself some real estate, if we take the derivative of the velocity with respect to time, this is clearly just what the acceleration is as a function of time, and we're going to assume that the magnitude of this thing is constant, but the actual direction is changing. So this is the acceleration as a function of time, is going to be equal to, let me get my colors right, it's going to be equal to, we have this negative omega r, open the parentheses. So what's the derivative of this thing right over here? So the derivative of sine with respect to theta, we're just doing the chain rule here. Derivative of sine with respect to theta is going to be cosine of theta. So we get cosine of theta as a function of t. And then chain rule, we also have to multiply that times the derivative of theta with respect to t. And the derivative of theta with respect to t, I could write d theta dt here. But that, once again, is just omega. So that is just omega. And that's, of course, in the I direction. And then from that, next to that, we're going to have to take the derivative of cosine of theta of t with respect to theta. So that's going to be, that would be negative sine of theta, but we have a negative out front, so it becomes positive sine of theta as a function of t. And then we have to do the chain rule, the derivative of theta with respect to t. We have to multiply by this. And that, we could write d theta dt right here, but that, once again, is the same thing as omega. And all of that's being multiplied times the j unit vector. And then we can close our parentheses. So now let's factor out this other omega, and we get something interesting. We get the acceleration, our acceleration vector, as a function of time is equal to, if we factor out another omega, we get negative omega squared r. I'm just factoring out another omega, so that becomes negative omega squared r times, and I'll write it in parentheses here, times cosine of theta as a function of t, times our I unit vector, the color changing is the hard part here, plus maybe the same color, plus sine of theta, which is a function of t, times our j unit vector, Now, what is all of this business right over here? What is all of this business? If you just look at this part right over there. Well, r times this, especially if you distributed the r, that's exactly this thing right over here. In fact, if you distribute the r, you get exactly r cosine of theta as a function of t times our I unit vector plus r sine theta as a function of t times the j unit vector. So everything that I squared off in orange right over here, this is our position vector. This is our position vector as a function of time. So all of that work we did, we just got a very interesting result. We got that our acceleration vector as a function of time is equal to the negative of our constant angular velocity squared, or I should say really the magnitude of our angular velocity, which we're assuming is a constant, the negative of that squared times our position vector. And just to be clear, angular velocity is kind of the pseudo vector. It tends to be treated like a scalar, especially when you're dealing in two dimensionals. In two dimensions like this, it's actually formally a pseudo scalar. But let's just go with this right here. We're assuming that this right over here is a constant scalar quantity. Now, how do we're very, 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 very close here. Now what we want to do is we want to relate this essentially the scalar version of it. So if we want to take the magnitude of both sides, so let's take the magnitude. So that we're saying the acceleration vector is equal to this constant times the position vector. So let's take the magnitude of both sides of this thing, the magnitude of both sides of this thing. So then we get the magnitude of the acceleration vector, which I'm just going to call a sub c, is going to be equal to, so you could say the magnitude of this negative omega squared. Well, when you take the magnitude, that's like taking the absolute value. In fact, the absolute value is the one-dimensional version of magnitude. That's just going to be a positive omega squared. We don't care about the direction. Sign gives us direction. We just care about the actual size. So this is going to be omega squared. Let me be clear. This is equal to the magnitude of negative omega squared times the magnitude of our position vector. The magnitude of omega squared is just going to be omega squared. You can get rid of the sign. And the magnitude of our position vector, we saw at the beginning of this video, is just r. It's just our radius. So this right over here is just going to be equal to the radius of the circle that we are going around. Now, we also know that angular velocity, or if we want to be particular, the magnitude of angular velocity is equal to the magnitude of our velocity, or another way to think about it is the speed of our object, divided by the radius of the circle that it is going around. So we can substitute that right over here. So if we square it, so this is going to be v over r squared, and we saw that in the video on angular velocity, times r. And this is all going to be the magnitude of our acceleration, which is really our centripetal acceleration, our inward directed acceleration. And so this is going to be equal to, and I think you see where this is going, this is equal to v squared over r squared times r. This r cancels out with the r squared, so you're just left with v squared over r. And you're done. The magnitude of the centripetal acceleration is equal to your speed, the magnitude of your velocity squared, divided by your radius. And we are done.